The next rule in our list is quotient rule. We've looked at what happens when you multiply two functions together, and we've already got a relationship between the derivatives of those two separate functions and the derivative of their product. This question is to do with what happens when we have a function divided by another function. So we call it a quotient of functions. Is there an easy way to find the derivative of f of x over g of x if we already know the derivative of the function f and the derivative of the function g? The first thing I want to point out is that we don't actually need quotient rule. So theoretically, you could answer any question that requires quotient rule with chain rule and product rule. Unless the question explicitly says using quotient rule, there's no reason why you couldn't use the other two. And the reason for that is quotient rule is essentially derived from the other two. That's what we're going to see as we work through. And we're going to start by doing an example that doesn't use quotient rule at all. And that will help us to see why quotient rule might be a useful shortcut to have. So you want to think of it not like an essential tool within your differentiation toolkit, but more like that nice to have, that handy extra helper that's going to make some tasks a bit more efficient and straightforward. And although you could do it without it, it's going to save you quite a bit of time to have this in your toolkit. That said, there are some times when instead of diving ahead into quotient rule, it's worth having a quick look at what you're dealing with. And even though it might look like a fraction, you might find that it's better off dealing with it as product rule directly. You'll see what that looks like in a second. Likewise, there are some things that don't immediately look like a fraction. We're going to get to things like tan x later on, where breaking them apart into a fractional form and then using quotient rule allows you to find a derivative that would otherwise be a little tricky. So let's start with this example, e to the x over x squared. Yes, we can differentiate e to the x and we can differentiate x squared, but by writing this as a product of two functions, we could think of it as a product rule question. So let's rewrite this as x to the minus 2 times e to the x, and then it just becomes straightforward product rule. So we write down x to the minus 2, we differentiate e to the x, that looks exactly the same. Then we write down e to the x and we differentiate x to the minus 2, minus 2x to the minus 3. And there we go, that's our derivative. We could write it slightly more simply. As we mentioned last time, if e to the x is ever a factor of your original function, it's going to be a factor of the derivative as well, because when you differentiate it, it sticks around. Now, let's look at another example. For this one, we're going to take something which is not quite so straightforward to differentiate directly with product rule, but we're going to see what would happen if we just plowed ahead and we used product rule and we used chain rule if necessary to sort things out. We can differentiate sine x, it differentiates to cos x. We can differentiate ln x, that differentiates to 1 over x. But what about 1 over ln x? Or ln x to the power of minus 1 might be a more helpful way of writing it. The issue with this is there's no obvious way of differentiating 1 over ln x, not like there was with x to the minus 2, that uses the same rule as x squared. But with ln of x to the power of minus 1, we have to recognize that now we have a chain rule situation. Well, that's not the end of the world. We can deal with chain rule. Anything to the power of minus 1 will differentiate to minus the anything to the power of minus 2, provided we also multiply by the derivative of that anything, whatever was inside. So let's try it. We start by writing down ln x to the minus 1 unchanged and multiply it by the derivative of the other term, the sine x differentiates to cos x. And then we differentiate the ln x to the minus 1 using chain rule, so there's quite a bit going on in that section, and multiply all of that by sine x unchanged. So this entire section here, this represents the derivative of ln x to the power of minus 1. We've got the ln x with the minus 1 coming out in front, and then the power itself dropping down to minus 2. And then afterwards we multiply by the derivative of the term inside, the inner function, which was ln x, so its derivative 1 over x appears as a factor there at the end. So it's possible, but it's a bit messy. And it might be nicer to simplify things a little bit. So what I'm doing here is using the fact that ln x to the power of minus 1 is a factor. I mean, you could even argue that ln x to the power of minus 2 is a factor in some sense of both terms. So if we pull that out as a common factor, or write both over a common denominator, then we can write this in a slightly different way. You might argue that it's not much simpler, but we're going to see how it ties in nicely with the rule we're going to come up with in a moment. You might want to compare it with the first example over on the left, where we had e to the x over x squared initially, and at the end we had something involving e to the x on the top and something with an x cubed on the bottom at the end. Here we've ended up with the square of the original denominator for ln x. Ln x becomes ln x squared, but then ln x and sin x also appear in the numerator along with 1 over x and cos x, the derivatives of the numerator and the denominator. If we'd chosen to rewrite what we've got on the left-hand side with e to the x over x squared in a slightly different way, we could make it look more obviously along the same lines as this one. But what we're going to do next is look at a more general version. So let's see if we can generalize that product and chain rule approach that we used in that question. We'll go quickly through that other example. We had sin x over ln x. We broke it apart into the denominator to the power of minus 1 multiplied by the numerator. Then we used product rule to deal with that product of two functions. And when we came to the bit that was something to the power of minus 1, we used chain rule to deal with that. Then, and we're going into slightly more detail with this step now, we're writing both terms over a common denominator. Cos x over ln x is essentially what this very first term here represents, and cos x over ln x can equally well be written as cos x times ln x over ln x squared, which allows us to have a common denominator with both parts. Once we've got that, we can put them all together, and this is the final answer that we got before. Now, look at what happens when we try that with the general case. We'll have f of x over g of x. If we try this, and you'll be able to follow along with the color coding, we have the denominator to the power of minus 1 multiplied by the numerator. Well, we can use product rule to break that all apart. And once we've done that, we can use chain rule inside that. Remember, the g of x to the power of minus 1 becomes minus 1 lots of g of x to the power of minus 2 multiplied by the derivative of g of x. When we sort all of that out, again, we get this common denominator of g of x squared. And we can write both separate terms like that. There's a minus there in between the two. That minus comes from the same place it came from in the previous example. The negative sign comes from the minus 1 that came down from the power of minus 1 that originally happened because of the way we rewrote the denominator. And that's the same no matter what the function is. This was just any old function, we don't know what it is, but it had a power of minus 1. Therefore, when we differentiate using chain rule, we'll see a power of minus 1 come down in front, and therefore we'll see this negative appearing here. The powers are the same as well. The power of minus 1 becomes a power of minus 2. So all of this stuff with the fraction, this will be very similar for any other functions that you tend to work with. And now, of course, we've got common denominators. We can put the two fractions together. What we've got here is a generalized version of what we saw over on the left. We've got the original functions that were in the numerator and the denominator, both appearing in the numerator, but they're combined in a very similar way to product rule with the two functions' derivatives. So g of x and f dashed of x go together, f of x and g dashed of x go together. The difference is, instead of them being added together, they're subtracted. And that means the order matters, because you can't just switch around which you're thinking about, f, g, g, f. It makes a difference. X over e to the x is a very different function to e to the x over x. So it makes sense that the order should make a difference here. And we're also dividing by something. We've got this added complication of the denominator, the original denominator, g of x squared. So whatever that function was that was on the bottom, we have the square of that function appearing within the denominator of the new derivative function. This is quotient rule. Essentially, we apply the product and chain rule approach to the general case, something over something, f of x over g of x, and what pops out is this fairly nasty looking algebraic device, but This algebraic device will allow us to deal with a fraction of two functions that we can differentiate really quickly and easily. As long as we can substitute the terms into this, we don't need to go through the process of rewriting one of them as a power of -1, of using product rule and then using chain rule within it and then simplifying things through. We can jump straight to the end. This is like the quadratic formula, allowing you to bypass the process of completing the square. And just like with product rule, there are a number of different ways we can write this rule, and you'll probably have a particular favorite that you'll go with. Some of them are better written down, some of them are better spoken. Here's a fairly verbose way of saying it in words: bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared, the square of the denominator. There's a slightly pithier version here, which I tend to mutter to myself when I'm in the middle of one of these questions: bottom d top minus top d bottom over bottom squared. And if you can get that into your head, then it saves you needing to look at the formula book. But you'll be pleased to hear that this formula, in this form more or less, the version we've just got up here, is provided for you in the formula book. So this is the f of x, g of x version, and you can see it looks messier, but when you break it apart and look closely at what's going on, this should look fairly familiar because it's got similar terms to the product rule. We can use the UV approach, just like we did with product rule. We could say dy by dx is going to be u dv by dx minus v du by dx all over v squared. And again, just like with product rule, we could replace dy by dx with the shorthand y prime or y dash. And similarly with dv by dx and du by dx. So we get this. Looks a little neater. It's going to be quicker and easier to jot down and relatively quick to apply without it looking too crazy. We've got the bottom multiplied by the derivative of the top, that's v u dash. Take away the top multiplied by the derivative of the bottom, u v dash. And then on the bottom, we're dividing by the original denominator, v squared. It's important that you remember the order matters. We don't have the same symmetry we got with product rule. With a product, u times v is the same as v times u, but with a quotient, u over v is absolutely not the same as v over u, unless u and v happen to be identical. So you've got to watch out for that. There will be a negative sign, and it matters which term comes first. vu dash minus uv dash is the opposite of uv dash minus vu dash. They're negatives of one another. And of course, you've got to make sure you're dividing by the denominator squared, not the numerator squared. Here's what it looks like in the formula book. You flick to page 6, which is where your year 2 differentiation results will be provided for you. And in addition to the first principles formula, you've got a few results about trig that we'll come to in a moment. And we've also got right at the bottom the quotient rule. It's not listed as such, but it's given here as if your function happens to look like f of x over g of x, then the derivative will end up looking like f dashed of x, g of x minus f of x, g dashed of x, all over g of x all squared. So it's written very similarly to the version we've got up here. And if you want to learn it like that and use it like that directly from the formula book, then at the very least you'll have the right format in front of you in the exam. You'll know what you're looking at. Okay, let's try a quick example. Find dy by dx for the following curve, y equals e to the 2x over cos x, and hence find the x coordinates of any stationary points. So we recognize first of all that this is a quotient rule problem. We glance at the formula book and we recognize that we've got the formula for quotient rule. You might remember it in your own pithy way so that you can easily apply it. But it's really important that, just like we were talking about with product rule, you are clear on what u is and what v is, or what the top and what the bottom are, f of x and g of x, so that you can get them the right way around. One good way to do this is to write out the quotient u over v, and write out the terms u and u dash, v and v dash for each one. Each one of these is its own miniature differentiation problem, but they shouldn't be particularly complicated ones, particularly if you're reasonably comfortable with a bit of chain rule, like we've got here, e to the 2x becoming e to the same thing, e to the 2x, multiplied by the adjustment factor, the derivative of 2x. And then cos differentiates to minus sign. That's one of the standard results that you'll be learning. And once we've got all 4 of those terms written out in front of us, all we have to do is make sure we put them in the formula in the right place. So I've written this formula out as VU dash minus UV dash over V squared. We just pick out the appropriate terms from the little set of 4 that we've got directly above. So we have a cos multiplied by the derivative of e to the 2x, and then we have e to the 2x multiplied by the derivative of cos. We subtract one from the other, we divide by the square of the denominator, so we're dividing by cos squared x. And then, ideally, we simplify a little bit. So we can pull out e to the 2x as a common factor, and we'll leave it looking like this. You could write it in a few different ways, but you'll find that if you're interested in finding stationary points, we want to find the places where the derivative dy by dx is equal to 0. It's helpful to have it in some kind of single fraction factorized form. So that's where we come to the stationary points bit. We can look at when stationary points occur. It's when the derivative is 0. We can see that this entire big fraction being 0 is effectively the same as saying the numerator needs to be 0. And the numerator will only be 0 if one of the factors of the numerator is 0. E to the 2x is one of the factors, but that cannot be 0. Therefore, the only way we're going to get solutions is if the other factor, 2 cos x plus sin x, is equal to 0. A little bit of quick rearranging, taking away sin x from each side and dividing through by cos x and vice versa. You can turn this into tan x equals minus 2. Once you've got that, we have an entire family of solutions. There are loads of stationary points for this curve, because every single time 2 cos x add sin x equals 0, we'll have a stationary point. Every time tan x is negative 2. And luckily, this is a fairly nice one to get a general solution for. You won't usually be asked for a completely general solution like this at A level. It's more the sort of thing you'll see in further maths. But it's worth noticing that if you've got a single solution for tan x equals a number, then you can get all the solutions just by adding an integer multiple of pi. We can add 0 pi and get minus 1.107, or we can add 1 pi, or we can add negative 3 pi, or however many pi's we like, and we will get any and all of the values of x for which tan x equals negative 2. Tan is an easy one to do like that, because there's no symmetry you need to worry about. It's all just about the period of the graph. You're just adding 180 degrees or taking away 180 degrees to jump from one solution to the next solution along. Now, it's worth looking at the graph here. I tried sketching the graph in GeoGebra, and we got this green one. And it really doesn't look as if there's many stationary points. We get one at minus 1.107, it looks like. But then, according to our calculations, we should have another one. We should have another stationary point every single time tan x equals minus 2. So there should be another about pi below this, and another pi below that, and then others to the right as well. The other thing I was surprised to be missing was asymptotes. If we think about the original function, e to the 2x over cos x, it should have an asymptote every single time cos x equals 0. Now, don't be fooled by the graph. Don't get overly dependent on whatever the technology gives you, because it's going to be limited by the fact that it's computational. It's a numerical method that's being used to represent the graph. It's throwing things into a calculator, getting a result, and putting it on the graph, and then joining the points with lines. Now, we know that cos x will be 0 at nice regular intervals. So there will be an unlimited number of asymptotes on this graph. To illustrate that, I tried putting in e to the x over 2 over cos x instead of e to the 2x over cos x. That's a graph that still grows exponentially, but a bit more gradually than e to the 2x. And it turns out you can see pretty well, certainly for this bit I've zoomed in on, you can see where those asymptotes are taking place. One of them in the same place as e to the 2x, the others should also be in the same place as e to the 2x over cos x. We just can't see them, and the reason for that is that the graph is changing so rapidly near the asymptotes. As it gets very, very close to an asymptote, it will change. It will suddenly shoot up towards positive infinity and then suddenly come back from negative infinity, but it does it so quickly that the graphing technology cannot really tell the difference. You have to zoom in quite a lot to see what's happening, and even then you don't necessarily get the full picture. So be a little bit cautious of the graphing software. It will only ever give you the equivalent of a decimal approximation, if you like. Just like the calculator can't tell you what root 2 is exactly, the graph cannot show you exactly what the function does. It'll only give you a pictorial representation. The last thing I want to do is look at trig functions. We've already got the derivative of sine and cos, but we've got 4 more trig functions, which now we've got quotient rule, we can actually tackle fairly efficiently. We can make use of the fact that every single one of those 4 is the quotient of 2 functions which only involve sine and cos. So, for instance, tan can be written as sine over cos, sec can be written as 1 over cos, which may seem a bit strange, but it's a trivial case of quotient rule. The upper function 1 differentiates to 0, so we can use that without a problem. And cot and cosec will do the same sort of thing. Once you have had a go at these, see if you can simplify your answers in such a way that they don't involve any fractions. So if you end up with 1 over cos x in your answer, turn it into sec x, for instance. When you've had a go at those, continue with the video and I'll show you the answers. So for tan, things work out quite nicely. The bottom multiplied by the derivative of the top is cos multiplied by the derivative of sine. So we get cos times cos, cos squared. And then we're taking away sine times minus sine, which means we're adding sine squared. And we end up being able to make use of that identity, sine squared x and cos squared x equals 1. So we end up with sec squared. Tan differentiates to sec squared. Sec, if anything, seems like it should be simpler because 1 differentiates to 0, but at the end we get a sine on the top instead of a 1 on the top. But still, with a bit of work, we can turn this into something that doesn't involve fractions. Sine over cos is tan, and 1 over cos is sec, so we can break apart our fraction into 2 simpler looking fractions multiplied, and each one is its own trig function. For cot and cosec, things are similar. In fact, for cot, because the cot function, cotangent, is the complementary function that goes with tan, it's pi by 2 radians, or 90 degrees if you prefer, out of phase with the tangent function. And therefore, predictably enough, its derivative is 90 degrees, pi by 2 radians, out of phase with the derivative of the tan function. It's worth remembering, anytime you're dealing with calculus and trig, we are always in radians. So although we might talk about 90 degrees informally, anytime we're dealing with these, we're differentiating or integrating, we have to be in radians, because radians is the format within which all of these results hold. If you wanted to do it in degrees, you'd need to bring in some messy chain rule and end up multiplying things by pi or 180 to make the adjustment. We don't want to worry with any of that, so we always work in radians. Cosec gives us a similar sort of result to sec, which is expected again because sec and cosec are complementary functions, secant and cosecant, just like sine and cosine, and tangent and cotangent. So they're going to be pi by 2 out of phase with each other. But this one's got a negative sign, and you want to be careful with that because most of them don't. One of them does. You want to watch out that you don't forget which one it is. Luckily, all of these results are provided for you. So the formula book looks like this. In fact, the formula book very helpfully gives not just all 4 of these additional trig functions, but it gives the quotient rule directly underneath them, which is a nice clue, because although you don't need to memorize them, you do need to be able to prove them. And the way you would prove each of them, as you've just seen, is using the quotient rule. So anytime you're asked to prove one of these, show that the derivative of tan is sec squared, then you would glance at the formula book and notice that you've got the quotient rule there. You can apply the quotient rule to those. It's also nice to see that you've got a little reminder of mini chain rule. If you have tan of kx, then the derivative is just sec squared of kx, but then you multiply by the adjustment factor, the derivative of kx. Now you should be able to deal with both of the next 2 exercises, 9e and 9f. 9e involves quotient rule primarily, and 9f incorporates the trig results that you've seen. The only questions you don't need to worry about are 8, 9, and 10 in that last one. That's because there are a few results, inverse trig results, which are optional to the course. I'm going to put up a short video on those for those of you who are interested, because there's nothing in there that you can't deal with, but it's nothing you need to worry about because those particular parts are no longer examinable for A-level. They'll come into further maths, and they only involve an application of chain rule, so they're worth playing around with, but they're not necessary, so you don't need to do those questions if you don't want. One final thing, I mentioned being careful with your negative signs. There is an error of that sort on page 247, where the book quotes the results that we've just been proving on this page. So watch out for that, keep an eye out, and if your book is old enough to still have this error, then you can fix that for yourself.